Hey there, everyone. In today's teaching lesson, we are going to focus on optimization, and we're going to be doing calculations to find the most efficient economic profit as well as efficient work schedules. So training schedules where people have to work certain shifts. It could be at the grocery store or the warehouse, it doesn't matter, but people have to work at a specific shift, and there could be constraints. Some people maybe can't work on the weekends, maybe somebody can't work Mondays and Wednesdays, or whatever the case may be. So we'll set up a couple scenarios focused on economics and then worker schedules. So why do we need optimization for product pricing? It helps us to find the ideal price between charging too much for a product and having people not buy the product. They don't want to make the purchase because it's too expensive, or charging too little and all the products fly off the shelves, and then we liquidate everything and everything's gone, but we could have charged more. So we left some money on the table because we did not charge more, because we didn't know what the optimal price point was going to be between enticing people to buy the product and the alternative is charging too much and turning them away. Okay, so you have to consider maximizing revenue for sure. Any kind of market positioning, perhaps what the competition is doing. Maybe the competition is lowering their prices. Maybe the competition is raising their prices, and you can lower yours and entice people to buy your product over what the competitor is selling, right? Cost management, it's called demand elasticity, like how elastic is the demand? How flexible is it? In some cases, demand is very inelastic. You can charge as much as you want, and people just keep paying it, usually for luxury products, right? And sometimes demand is very elastic, usually for necessities, food, groceries. If you charge too much, somebody's just going to go down the street and go to a competitive grocery store and get their food there, right? So when you understand all of these attributes, you can create a competitive advantage for yourself. And one thing I love about optimization is really it doesn't take any investment in hardware or software. You don't have to do millions of dollars in upgrades. You don't have to build out your architecture infrastructure. All you have to do is understand how your business operates today, optimize that process, and then reap the rewards, right? So for very little investment, maybe close to zero investment, you don't have to invest $500,000 or millions of dollars. You can generate a significantly higher profit just by optimizing your current business process, right? So we're going to look at two scenarios today, how to do that. So I'm going to create a data frame right here and Control Enter to run the cell. And I'm going to share all this source code with you guys. When I post a video, it'll have all this code. You can copy and paste it, run it in your own Jupyter Notebook environment, and see exactly how it works. So I'm not going to go through all the nuances and all the details of everything, but I will highlight a couple critical items here. The scipy.optimize library is going to help us do the lift and help us optimize the best price point to charge here based on demand, right? Again, if we charge too much, people won't buy it because they're going to perceive it as too expensive. And if we charge too little, we'll sell probably everything, but we leave money on the table because you could have charged more and people still would have bought the stuff, right? So we have our customer ID, SKU category, and SKU. I'm more interested in SKU because that is relative to the product. The category can be repeated. You can have whatever it is, like frozen items, right? And that can contain ice cream, frozen pizza, frozen broccoli, right? That'd be the SKU category, but the SKU number would be the item specific thing that you're selling, right? So the item specific detail is as granular as we're going to get. So we're going to look at SKU price and demand, and we are going to create a very simple function here called price. We're going to return the maximum base demand and price sensitivity times the price, right? Or zero, or just give me zero if there's no change. If there's no change in the price that we're charging now, it's going to be zero. It's going to stay the same, okay? And then we look at prices, demands, and the overall price times demand, okay? And this is a negative number because we're minimizing. In the scipy optimized world, there's no maximize. You only minimize, where you take the negative, or if you just remove the negative, by default, it will maximize. But it doesn't really have a maximization function. It's just a minimizer or not minimizing. By default, it's maximizing. So I'll set some bounds here with a constraint of 1. And the length is a data frame, so it's going to loop through all the items in this data frame 0 through 18, so it's 19 items because it's 0 based. All right, and we will we'll minimize the total profits, but again, maximize, because we don't have the negative sign here. If we had the negative sign here, that's actually minimizing. This would be a minimization problem. If I put a negative sign there, we're actually maximizing, but there's no maximize per se. So we just take a positive minimum. It's a little, I know it's a little foreign the first time I saw it. I was like, what the heck are you talking about? But that's how it's done. So we run this, we get the output here, Control Enter. We'll see a couple things. Convergence, okay, and success is true. That's the second line. Status is 0. There's no errors. The function is negative 0.88. That's the minimization objective function that we set. It took 2 iterations to get there. NJEV is 2, and NFEV says 40. So that is the function had to run 40 times to find the solution. Okay, had to run 40 times. And the gradient descent was actually just done twice to find the optimization. So 40 iterations to find the optimal price, to maximize price, and 2 runs on the gradient descent. Okay, so we have percentage improvement, the after profit, and the profit before times 100. Right, we're taking profit before divided by profit before times 100, and then the profit after is being subtracted from this result right here. Okay, so everything within the not the quotes, within the brackets, yeah, the curly brackets is done first, and then the division is done after that. Right, so that's the order of operations in the math world, and then we go down to optimize price. And we're going to print the result. Okay, so the optimization is done in the prior cell. We're going to print the result and get all the updates printed over here. So run it, Control Enter. So we have the profit before, profit after, optimal price, and then a percent improvement. So this is what I'm focusing on right now. Percent improvement. That's the after minus the before divided by the before. And you do that for anything, like a stock price too. Like if you buy a stock at 100, it goes to 120. To find the relative change, it'll be 120 minus 100 divided by 100, because it's always n minus beginning divided by beginning. That's the standard way of doing it. You can think of n minus begin divided by begin. If you buy a stock at 100, it goes to 120, you have a 20% profit, right? So percentage improvement, this is what I'm looking at here. We have, in the first case, 2.6%. NaN means 0. That just means there's no change. So the optimal price is 32 on row 1. This is actually 2 because it's 0 base. Remember, we start with 0, but that's kind of the first row. So 32, no price change. Price after is 0. So 32 was the optimal price. So that was set fine. These over here, 28 down to 14, there's no improvement. These are all optimal prices. So pretty close. This one, row number 9, which is really 10, optimal price was 5.9. Oh, the original price was 5, so we can get a small gain there. That's 9, and the gain was about 2%. And let's look at 18. That's a pretty big one, pretty big jump. Oh, actually, okay. So the price for 18 originally was 8. The optimal price, the original price is 8. Optimal price is 5. The profit before and profit after changed a little bit. So we were charging originally too much. So the optimal price is too much. Should move more products. It should be at 5.9, not 8. Okay, and let's say the total overall profit increases, right? That's what I want to know. So we know the line by line improvement, the total overall improvement is 21%. So that I think is pretty cool. Now we've used a little mathematics, taken just a small increment of time to understand how all this works. Made no investment in infrastructure, architecture, no capital build, no we have to build a new warehouse, or we have to build an addition onto the store to handle more inventory or whatever. No, it's none of that. All we had to do was use some brain power, sit down and figure out how to solve this problem, and we just improved our profits 21%. That's pretty huge, I think. Without doing a whole lot of legwork, it was just brain power, We made the business more optimized, right? So that's pretty cool. That's what I love. That's what I love about these problems. You don't have to invest a lot other than a little time and a little know-how and generate a significant boost in your bottom line here just because you're operating more efficiently now, or you're pricing your items more efficiently. So they're going to move faster. You're going to sell more, or maybe sell a little bit less, but you're going to charge more for that product. So it's still optimizing the way that you do your business. Okay. So let's look at another similar type of problem, but instead of economics or price-based, this is a scheduling type of problem. So this is good for creating efficient work schedules where people aren't sitting around bored because it's too many busy. There's too many people not working, so people aren't busy. Okay, we eliminate that. We don't have too few people, so customers are frustrated because they can't get what they want. We don't have that. We're finding a balance between how many workers are enough and how many workers are too much, right? So it's a delicate balance between that and keeping the workers happy too. Like they want to make the money. They don't want to be cut out of the equation because some guy is making double what another guy is making. Maybe give the guy that's making more money fewer hours. Maybe he's more senior person and he's more expensive, but the business has to operate at a net profit margin too, right? So if some guy is very expensive, we can still keep him on the payroll, but we'll give him less hours. If some guy is a little bit less expensive, but he can do essentially the same job as a more expensive guy, we give that guy more hours, right? And we're still satisfying the constraints of customer satisfaction, giving people enough time so they're getting paid. If you don't pay your employees for a couple of weeks, they're probably going to leave, right? So we're focusing on the objective functions, the constraints, cost efficiency, any kind of compliance with labor laws, things like that, employee satisfaction. Again, if you cut your employees out of the equation, they're probably going to be gone in a couple of weeks if they're not getting paid. If they get no hours, they want to get hours too, right? They want to get paid too. Operational efficiency, and then resource allocation has to be optimized too, right? And that helps relieve stress across different shifts. You don't over-employ or under-employ, right? So that's what we're looking at. Let's jump into it. This is linear programming. Now, the last example is scipy.optimize. That's more of a non-linear optimizer, right? It creates a matrix of all possible combinations of outcomes and then finds the optimal outcome for you. This is more of a linear programming. So you can solve this with just pencil and paper and looking at the problem of all the outer bounds of constraints, and you draw lines that will cross over each other. And then you find the optimum point of all the crossover lines, right? Or you would create sort of like a weird looking maybe hexagon shape or something, and you look at the intersections of those lines, and where those lines intersect, that's going to be the optimal point. So this is more of a linear style programming. The last one was curvilinear. So we have different shifts, morning, afternoon, evening, different workers. We have 5 in this case, and this can be anything, right? This would be relevant to your specific grocery store or warehouse or retail outlet. I'm trying to make these examples as generic as possible. The last one was kind of based on a grocery store. This one is actually still based on a grocery store. But it could be anything, right? Use your imagination, and you would just plug in your shifts, your workers, and so on and so forth, right? So we have the cost, the person working, and then the shifts, right? And then how much that worker would earn for that shift, right? And then we have the second worker and the third and the fourth and so on. Then we have the man. So we need 3 workers in the morning. We need 4 in the afternoon. And we need 5 workers in the evening. So let's say this is a grocery store example. In the morning, there's not too many people shopping for the groceries, probably retired people. In the afternoon, you might have the first shift workers coming in to get some food. Probably the 9-to-5ers are not shopping in the grocery store at this point. Although maybe if you're in downtown Manhattan and there's a Whole Foods down there, they could be shopping now. But I'm just thinking generally across the United States, you wouldn't have too many 9-to-5ers doing their grocery shopping in the afternoon. It'd probably be more in the evening, so you'd schedule more workers in the evening. So you have 3, 4, 5 workers. Let me go ahead and refresh this. Control Enter. Okay, and we're almost done here, so just hang with me. So we have the shift variables over here. The problem, this is a linear programming. We're taking all the costs, functions, the workers, right, and the scheduling, the W and the S, and we're looking at all the possible shifts and we're creating a loop for W in workers, for S in shifts. So it's actually 2, right? Again, like the scipy.optimize, we're creating all possible combinations, right? And we're trying to minimize all the combinations of satisfying all these work conditions over here, the cost for each worker, and then the number of workers that we need for each shift, right? So those are the two problems that we're trying to solve. And we go ahead and hit, I think I already did this, I already hit it, okay. So then we get the final output here. Dennis works the evening shift, Jane works the morning, Jane works the afternoon, and this is just the initial schedule. You can negotiate with your employees and make sure everything's copacetic there. But this would be the initial recommendation from the linear programming problem solution, optimized solution, right? And the total minimum cost to the grocery store owner is $1,980. Now, if you did not minimize this, then these costs would be swinging all over the place because it would be very random, right? Like Dennis might get $550, right? So you're paying a premium for him. Maybe not, maybe $200 and $500, but now you're minimizing the whole problem. So Dennis is working the evening shift, and he only gets 1 shift. Now let me go back and see that. Why is that? Well, there you go, right there. So Dennis is probably going to work for, I'm guessing, 4 or 5 hours in the evening. So you give him 1, but you're not paying him for the whole afternoon. He'd make $550, or the morning, where he'd have more hours and you're paying him $500. So he has 1 shift. That's his cheapest shift, $200, and you're done. So you can see how this thing works. And it costs for the whole week, the grocery store owner for salaries, $1,980, and that's guaranteed to be the minimum cost of the grocery store owner. So pretty cool. You might run into problems with Dennis saying, well, listen, I need more work. You're only giving me 1 shift in the evening. That's just not enough. So then you can play around with it. You can give Dennis 1 more shift. Obviously, like he's getting 1 because it's $200. It's cheaper for the grocery store owner. That's why he's getting just 1. But you can give him more expensive shifts. You can make an exception for Dennis. They can trade days. Again, this is optimizing this mathematical problem. So you might have people coming back and saying, well, I need more hours. I have a family to take care of and so on and so forth. But that's more of a political or socioeconomic type of problem that you're trying to solve. And you want to keep people happy. I'm not saying like give Dennis $200 and that's non-negotiable, but this is solving the problem. You're optimizing the problem of how to minimize the cost for the grocery store owner. So hopefully you learned a couple new things here with this exercise. I'm going to save the code, post it with the video. You'll have access to all this. You can copy, paste it in, and run it. And I think you will learn a ton. Hopefully that was enlightening. And yeah, that's pretty much it. Thanks for your time, everybody. Have a great day.